All right, so these notes are going to cover sections 4.1, 4.2, and it deals with the system of linear equations. So I'm sure we've been introduced to equations before, but what are they? A system of equations just means it's more than one equation. Okay, it's two or more. In this class, we'll only deal with two equations, but it also deals with their graphs and perhaps those same equations in function form. There are three different types of solutions that you're going to see, and their graphs that represent them. You see here, you want to have this information in your notes. First of all, remember we said that we'll be dealing with two equations, right? So let's say we have equation 1 and equation 2. Both of these equations are going to have their own graphs. When you graph the line of equation 1, you're going to see a line. The line of equation 2, you'll see that line. That point, if you were to graph those two lines and those two lines intersected each other, that point where they intersect is the solution to the system. You also describe that solution as being consistent and independent. So if you graph the two lines intersect, you have one solution at that point of intersection, and that solution, of course, is going to be an ordered pair. So you write that ordered pair as your solution. You'd also describe it as being consistent and independent. If you graph those two lines and they never touch each other, those are called parallel lines. So if you get two parallel lines, they never touch each other, that means you have no solutions. And you describe the graph as being inconsistent and independent. If you were to graph those two lines and you wound up with the same line for both equations, like they're right on top of each other, two of the same line, that means there are infinitely many solutions because they're constantly going to touch each other. They're overlapping each other. And we describe the graphs as being consistent and dependent. So these are the three types of solutions you're going to see in this section, either intersecting lines, parallel lines, or a single line for both equations. And we describe the graphs as being consistent if you see intersections. If there's only one intersection, you would say it's independent. If there are several, infinitely many solutions, then you would say it's dependent. Of course, if the lines never touch, if they're parallel, you would describe the graph as being inconsistent and independent. So let's look at some examples. Starting with the first problem, we want to consider this linear system. We got negative 6x plus 7y equals 29 and 3x plus y equals 16. Now to solve this system, we want to find if there's a point of intersection. We want to know what is that ordered pair if it exists. In this question, we're given an ordered pair, 5, 1, and we want to know if it is a solution to that system. And if it is, then we should be able to substitute 5 everywhere we see x and 1 everywhere we see y into both of these equations. All right, this solution would have to be true for both equations in order for it to be a solution to the whole system. So we'll start with the first equation, negative 6x plus 7y equals 29. And what we did was we substituted 5 for x and 1 for y. And when we do that, we simplify over on the left side of this equation. Negative 6 times 5 gives us negative 30. And 7 times 1 gives us 7. Carry down our equal sign in 29. And then we'll solve this here. Negative 30 plus 7, is that equivalent to 29? No, that's not true. So negative 30 plus 7 does not give us 29. Therefore, 5, 1 is not a solution to the system. We just stop there. We wouldn't even go to the second equation. All right, the next problem, we want to consider this graph of a system here. And we already know when we have intersecting lines that there's one solution. what is that solution is what we're being asked. So we simply find that ordered pair over here on our x-axis. We want to count the number of spaces that we move, and on the y-axis we want to count the number of spaces that we move. And to get to this point down here, we go to the right 1, 2 spaces. That's 2 on the x-axis. So we put 2 in that position of our ordered pair. And we also move down 1, 2 units. So that's -2 on the y-axis. The solution to the system is going to be 2, -2. For the next example, we want to solve this system by graphing. And the way that we're going to solve the system by graphing is, like I said before, each of these equations are going to have its own graph. So we have to write the equation separately, and then we're going to graph the two lines separately. So our first equation, 2x minus y equals -3. We're going to solve this equation for y, get y by itself first, okay? And by solving that equation for y, what we do is we place that equation in slope-intercept form, the y equals mx plus b form. Notice when we have slope-intercept form, our y is positive. Currently, we have a minus in front of the y, so what we did was brought the y to the opposite side so that we can have positive y. So we moved our y to the right side, making it positive, and then we're going to add this 3. I'm going to move that 3 to the right side of the equation. So we're going to add 3 on the right side and add 3 on the left side. Now when we do that, 3's cancel on the right side of the equation. We just carry down the y. The y's will cancel on the left side, and we're left with 2x plus 3. Now it's in slope-intercept form. We just have the y on the right side, but this is the same as y equals 2x plus 3. After we solve for y, we can identify our slope. Remember our m and our b, our y-intercept. Our slope is 2, our y-intercept is 3. We want to write that slope as a fraction. So that slope is 2 as a fraction. We would write it as 2 over 1. So we'll remember to move up. That positive 2 tells us to move up 2 spaces and then right 1 space. We always start with our y-intercept. So on our y-axis, we're going to plot that point at 3. So here is our y-axis. We're going to move up 1, 2, 3, plot the point right here at 3. Then we use our slope to find a second point. We move up 2, right 1. So going up 1, 2, right 1, plot the second point, and then we connect those 2 points to create line 1, L1. Now we'll use those same steps, but following the steps using the second equation. The second equation is x plus y equals 6. And again, we're going to solve for y. This time, positive y is already positive on the left side, so we're going to subtract x from both sides of the equation. The x's will cancel on the left side, leaving y equals. And on the right side, we got -x plus 6. Remember that negative x means that our slope, the number that's in front of x, is negative. So as a fraction, that will be -1 over 1. That tells us we're going to have to shift down 1 space and right 1 space when we use the slope. Our y-intercept is 6. We start by plotting that y-intercept. So on the y-axis, we're going to go up 1, 2, 3, 4, 5, 6. Plot the point. We're right here at 6. And then to get the second point, we're going to move down 1, right 1. So move down 1, right 1. Notice we're touching that same point that we touched when we created the graph of line 1. Here's our graph of line 2. So that point where both lines cross, this ordered pair is going to be our solution. And that's at 1, 1, 2, 3, 4, 5. It's at 1, 5. This is our solution. Now the next example, we're solving the system, and then we're determining whether the system is consistent or inconsistent, dependent or independent. To make that determination, remember we base that based on the type of graphs that we get. If we get that one solution, we'd say consistent and independent. If we get the two parallel lines, no solutions, we'd say inconsistent and independent. And if we get that single line where there are infinitely many solutions, we'd say it's consistent and dependent. So we first got to graph the lines and determine which of these exist. Are they intersecting? Are they parallel? Or is there one line for both equations? All right, so looking at the first example, we see here x plus y equals 5 and x minus y equals 3. So this first equation, that x plus y equals 5 and x minus y, we're going to substitute these values and determine if we have independence or not. Now, we notice that both of our equations could easily be solved using a method called substitution. We can actually eliminate these by adding the top and the bottom equation. What do I mean by that? Remember, we had two separate equations. That first example we did, we graphed the lines to determine the solution. In this case, we don't have to graph the lines because that wasn't given to us in the direction. So we're going to just add the top and bottom equations, and when we do that, the y coordinates eliminate. They cancel each other out. 1y minus y cancels out, and we'd add 1x plus 1x to get 2x. On the right side of our equation, we have 5 plus 3 to get 8. And then we're solving. This is where our substitution comes in. We solve the equation for x. Divide both sides of this equation by 2, and we'll get x equals 4. Now, after we determine the x coordinate, right, that's the x coordinate of our solution, which is 4, we need to find the y coordinate. And to do that, we're going to substitute 4 back into one of these equations. It doesn't matter which one you use. You could use the first equation or the second equation. We just use the first equation. And remember that first equation was x plus y equals 5. But now we have a value for x, so we're going to substitute 4 for x. And we'll get 4 plus y equals 5. Solve by subtracting 4 from both sides of the equation, and we'll get y equals 1. So remember, we already had our x coordinate as 4. Now we have the y coordinate. This is the solution. And when we have one solution, we describe the graph of that function as being consistent and independent. So that's what we write as our answer. The ordered pair, and then describe the graph as being consistent and independent. All right, let's look at the next example. We have two equations, x minus y equals 4 and 2x minus 2y equals 4. Now, if we were to add these two equations like we did the previous example, 1x plus 2x will get 3x. Negative y minus that 2y will give us negative 3y. Neither of these would eliminate. So we want to rewrite one of these equations in a format so that we can cancel them out. Now you decide whether you want to get rid of the x terms or the y terms. Just remember you have to have one positive and one negative, and they have to be the same value. We chose to eliminate the x terms, right? And we have a positive x on top and a positive 2x on top. So in order for us to really eliminate these x coordinates, we need to make this top x term negative 2x instead of just x by itself. If this becomes negative 2x, then we can cancel them out. So we have to change this first term, but whatever we do to the first term, we must do to the other terms as well. So we're going to multiply everything in this top equation by negative 2. So that top equation is rewritten as negative 2 times x, that gives us negative 2x, negative 2 times minus y, that gives us positive 2y, And then negative 2 times 4 on the right side of the equation, that gives us negative 8. The second equation stays the same, so we just recopy it. Now we add the top and bottom equations, and we see negative 2x plus 2x, that cancels. Negative 2y minus 2y, that also cancels. So we get 0 on the right side of the equation. Equals negative 4 plus 4 gives us negative 4. This is not a true statement. 0 does not equal negative 4. So what that means is that we have no solution. And remember from our notes, when we have no solution, we describe the graph as being inconsistent and independent. All right, so we have two equations, 2x plus 4y equals 2, and negative 2x plus 2y equals negative 1. Again, if we add these terms as they are, nor the x nor the y terms are going to eliminate. So we're going to rework the bottom equation so that we can eliminate the x terms again. We already have opposite signs. We have a positive number and a negative number, but we want this to be a negative 2 in front of that x. So we'll multiply each of the terms in that second equation by 2. Rewriting this second equation, 2 times negative x gives us negative 2x. 2 times negative 2y gives us minus 4y equals, and on the right side, 2 times negative 1 gives us negative 2. The first equation stays the same. We add the top and bottom equations, and we see the x terms will cancel. Also, 4y minus 4y, the y's are going to cancel again. We get 0 on the left side of the equal sign. Carry down our equal sign, and 2 minus 2 is 0. Now, although we get 0, this time 0 does equal 0. That is a true statement. So no matter what number we substitute for x and y, we're going to get the same equation. These are the same. These equations will produce the same line, and we have infinitely many solutions. We describe this graph as being consistent and dependent. So it's infinitely many solutions. In the next example, we see 6x minus y equals 47, and 6x plus 7y equals 7. So our x terms, we have the same number, 6x, but we don't have opposite signs. So in order for these x terms to eliminate, we have to multiply everything in one of the equations, which is the top equation, by negative 1. So that top equation is rewritten. Negative 1 times 6x gives us negative 6x. Negative 1 times minus y, that gives us plus y. And then negative 1 times 47 gives us negative 47. The second equation stays the same, so we carry it over. And then we add the top and bottom equations. Negative 6x plus 6x, that cancels. 1y plus 7y is 8y. Carry down our equal sign, and negative 47 plus 7 gives us negative 40. We then divide both sides of this equation by 8, and we'll get y is negative 5. So after we get our y coordinate, we're not done. Remember, that's just one part of our solution. We've gotten the y coordinate. Now we got to go back and find the x coordinate. To get that x coordinate, we're going to rewrite one of the equations. Again, it doesn't matter which equation we use. We used the first equation that we started with. So that's 6x minus y equals 47. And for y, we substituted negative 5. Remember, a negative times a negative, this becomes addition. So we have 6x plus 5 equals 47. We're going to subtract 5 from both sides of this equation. The 5 will cancel on the left. We carry down 6x. And on the right side, 47 minus 5 gives us 42. We divide both sides of the equation by 6. The 6 will cancel on the left side, leaving x. And on the right side, 42 divided by 6 gives us our x-coordinate, which is 7. So our solution, that one solution we get is 7, -5. And remember, we describe these types of graphs when we have one solution as being consistent and independent. All right, so let's move to the next question. Now, in this particular example, we're going to use the substitution method. Now, we previously looked at some examples where we used elimination. Unless you're required to use elimination, you decide which method you prefer. Do you prefer the graphing method? Do you prefer elimination? Or in these examples, we'll work on some of them that deal with substitution, like this example right here. But before we get to that one, we have one more dealing with elimination. Our first equation, we have 3x minus 9y equals 81. And the second equation, we have 2x plus 6y equals -10. Now, if we were to combine these two equations as they are, that 3x plus 2x would get 5x. -9y plus 6y will get -3y. Neither of these would eliminate. We don't have the same numbers like before, so we would have to do a little bit more work. First, decide which of the terms you want to eliminate, and we're going to work with the x terms again. We have a 3x in that top equation, a 2x in the bottom equation. In order to eliminate these two, we need to get like terms, we have the same number, and opposite signs. So we find the least common multiple, the factor that both of these share. 3 and 2, the least common multiple would be 6. So I want to rewrite this equation so that I have a positive 6x in one of the positions and a negative 6x in another position, the second position. Find your LCD first. Find your least common denominator or your least common multiple. So LCM. We determined that it was 6 this time. So we want to rewrite both of these x terms as 6, one being positive and one being negative. So that top equation, to change that 3x to a 6x, we have to multiply by 2. But remember, you have to also multiply all the terms in that equation by 2. The bottom equation, the second equation, we're going to make this 2x a -6. So we're going to multiply each of those terms by -3. Now, our first equation, when we multiply that top equation, everything by 2, 3x times 2 gives us 6x. -9y times 2 gives us -18y equals, and 81 times 2 gives us 162. The second equation, we multiplied everything in that second equation by -3. So -3 times 2x gives us -6x. -3 times 6y gives us -18y. Bring down our equal sign, and -10 times -3 gives us +30. Now we can add the top and bottom equations together. So 6x minus 6x, that cancels. -18y minus 18y gives us -36y. And 162 plus 30 gives us 192. We then divide both sides of this equation by 36, or -36. And the -36's will cancel. On that left side of the equation, we carry down the y. And on the right side, 192 divided by -36. This gives us -16/3. This is our y coordinate. Remember, we aren't done. That's just one part of our solution. That's the y coordinate. We got to get the x coordinate by substituting. So you pick one of the equations. We just picked the first equation that we started with, that 3x minus 9y, which is 9y, equals 81. And for y, we substituted -16/3. So we have 3x minus 9 times negative 16 thirds equals 81. Now here, negative 16 thirds times 9, this 3 can be divided into 9 3 times. It's one way you could simplify it. And that negative in front of the 9 applies to the 3 now. So that's negative 3 times negative 16. And negative times negative, that gives us positive 48. Carry down your 3x in front, your equal sign, and 81 on the right side of the equation. Now we're going to subtract 48 from both sides of the equation. Carry down your 3x, your equal sign, and on the right side, 81 minus 48 gives us 33. We divide both sides of the equation by 3, and we'll get x equals 11. So here's our solution, 11 comma negative 16 thirds. And remember, we described those graphs with one solution as being consistent and independent. So this was elimination that we used here. In the next example, using elimination might not be the most reasonable use of your time. As you notice your equations, you have 2x plus y equals 15, and you already have y by itself in that second equation. You got y equals 3x. So we simply just take that value for y and we substitute it into the first equation. So where y is in our first equation, we're going to substitute 3x. So we rewrote our first equation, which was 2x plus y equals 15, but we substituted 3x for y. When we simplify on the left side of the equation, 2x plus 3x, we'll get 5x equals, and then on the right side, we carry down our 15, and then we just divide both sides of this equation by 5. The 5's will cancel on the left side, and x equals 15 divided by 5, or 3. Now we have our x coordinate. Remember, we're going to substitute again to get our y coordinate. So we recopied the second equation this time, that y equals 3x, and where x was, we placed 3. So we have y equals 3 times 3, or 9, and this is our y coordinate. Our solution is 3 comma 9. We describe the graphs with one solution as being consistent and independent. All right, for the next example, it's more appropriate to use the substitution method as well. And the reason why is because we have x by itself. We got x equals 8y minus 4 as our first equation. So we would take that 8y minus 4 and substitute it into the second equation. So you rewrite your second equation, substituting instead of x in front, we're putting 8y minus 4. Carry down your plus 8y and the equal 6. Now we're going to combine like terms. On this left side of the equation, 8y plus 8y is 16y. Carry down our minus 4, carry down our equal sign, and the 6 on the right side of the equation. So to solve, we're going to add 4 to both sides of this equation. The 4's will cancel on the left, and we'll have 16y equals 6 plus 4, or 10, on the right side of that equation. Lastly, you're going to divide both sides of this equation by 16. So 16's will cancel, and you'll get y equals 10 16ths. But this 10 16ths can be reduced. You can put it in lower terms by dividing both the numerator and the denominator by 2. So 10 divided by 2 gives us 5. 16 divided by 2 gives us 8. So we write 5/8 as our y coordinate. All right, we got part of our solution, 5/8. To get our x coordinate, we're going to go back and plug in the value for y into that first equation. Remember, that first equation was 8y minus 4. So here 8y minus 4, but we're substituting 5/8 for y. Now when we do that, these 8's cancel each other out, leaving 5. Minus 4, 5 minus 4 gives us 1. This is our x-coordinate. So here's our solution. It's 1 comma 5/8, which we describe as being consistent and independent. One solution, consistent and independent. All right, the next example, we see 4x plus 5y equals 6 and 2x plus 3y equals 4. This time, using substitution might not be the most reasonable use of your time because you don't have one of the variables already solved for themselves. We don't have x equals or y equals. So we want to work with our x terms. You decide whether you want to work with the x terms or the y terms, and we're going to eliminate these x terms. We have our x terms as 4x and 2x, so we want them to be the same. We have this positive 4 as our top x term. That bottom term can be converted to negative 4 if we multiply that positive 2 times negative 2. So that's what we're going to do. Just remember you also have to multiply all of the other terms by negative 2. So the top equation stays the same, 4x plus 5y equals 6. And the second equation, we multiply each of those terms times negative 2. You get 2x times negative 2, that becomes negative 4x. 3y times negative 2, that becomes negative 6y, equals, and 4 times negative 2 on the right side becomes negative 8. So now we're going to add the top and bottom equations. 4x minus 4x, that cancels out. And 5y minus 6y gives us negative y, equals 6 minus 8, negative 2. Now remember, this negative in front of the y is the same as negative 1y. We got to get rid of that negative sign. So we're going to divide both sides of this equation by negative 1. That cancels the negative in front of the y, leaving y, equals negative 2 divided by negative 1 is positive 2. And now we have our y coordinate as 2. We're going to go back and substitute that y coordinate into this first equation. So here where y is, we're going to plug in 2. So instead of 4x plus 5y, we have 4x plus 5 times 2 equals 6. We're simplifying. 5 times 2 gives us 10. Carry down our 4x and the 6. And then we're going to subtract 10 from both sides of this equation. The 10's will cancel on the left side, leaving 4x. And 6 minus 10 gives us negative 4 on the right side. So we're going to divide both sides of this equation by 4. And we'll get x equals negative 1. So now we have our solution. That one solution is negative 1, comma 2. We describe the one solutions as being consistent and independent. All right, in the next example, so we have one that deals with fractions and one that deals with decimals. Now, when we're working with fractions, just like when we were solving single equations, we had to get that least common multiple in order to eliminate that fraction, the denominator. So we have 2, 3, and 6 in the denominator of our first fraction. We have 5, 4, and 10 in the denominator of our second fraction. So this LCD between 2, 3, and 6 is going to be 6. So first we're going to distribute 6 to each of the terms in that top equation. And when we do that, that 2 will cancel with the 6, leaving 3. 3 times 1x gives us 3x. Our first term, 3x. That 3 can be divided into 6 2 times. So we have minus 2 in the numerator times the 1, and the y gives us negative 2y as our second term. And then on the right side of the equal sign, 6 and 6, those two cancel each other out, leaving 5 on the right side of the equation. 5, 4, and 10, that least common multiple is 20. So we're going to distribute by multiplying each of the terms in that second equation by 20. 5 can be divided into 20 4 times, and 4 times that numerator, 1x. 4 times 1x gives us 4x as our first term. The second term, we have minus 1/4 y. That 4 can be divided into 25 times. So that becomes minus 5 times 1y in the numerator. That's negative 5y. And then 10 can be divided into 22 times. 2 times the numerator, 2 times the 15, gives us 30. So after we remove the fractions, we're left with 3x minus 2y equals 5, and 4x minus 5y equals 30. We still want to eliminate our x terms, so we now have to find that least common multiple between 3 and 4, which is 12. So we want one of these terms to be positive 12 and the other one to be negative 12. We chose negative for the top term. So we multiply everything in that top equation by negative 4 and everything in the bottom equation by positive 3. So this first equation is rewritten as negative 4 times 3x, that's negative 12x, and negative 4 times negative 2y, that's positive 8y, equals 5 times negative 4, this is negative 20. The bottom equation, we're multiplying each of the terms by positive 3. So 4x times 3 gives us 12x. That's our first term. And negative 5y times 3 gives us negative 15y, equals 30 times 3 gives us 90. Now we want to add the top and bottom equations together. Negative 12x plus 12x, that cancels. 8y minus 15y gives us negative 7y, equals, and on the right side, negative 20 plus 90 gives us 70. At that point, we divide both sides by negative 7. And when we do that, the 7's cancel on the left side of the equation, and 70 divided by negative 7 gives us negative 10. This is our y coordinate. So we have the y coordinate as negative 10. We're going to substitute this y coordinate into the first equation. So we just use this 3x minus 2y, and we substituted negative 10 for y, equals 5. So we simplify here, 3x minus 2 times negative 10, that gives us positive 20, equals 5. So we want to subtract the 20 from both sides of the equation. The 20s will cancel. On the left side, leaving 3x. And on the right side, 5 minus 20 gives us negative 15. Then we divide both sides of the equation by 3. The 3's cancel on the left side, leaving x. And on the right side, negative 15 divided by 3 gives us negative 5. So our solution, we have negative 5 as our x coordinate and negative 10 as our y coordinate. That's one solution. So we describe it as being consistent and independent. So we dealt with one problem with fractions. Now, when working with decimals, we want to remove the decimal, just like when we were working with a single equation. So what you see here is that each of your terms are in the tenths place. Like after the decimal point, we have one space. That's tenths place, tenths place, tenths place. Had that been 0.35 and 0.55 and maybe 1.22, we would have multiplied by 100 because those terms are in the hundredths place. But because it's in the tenths place, each of these terms are one space after the decimal point, we're going to remove the decimal point by multiplying each of the terms by 10. And we'll do the same thing in that second equation. Now, when we do that, what it does is it removes the decimal point. Move the decimal one place to the right. That's the same thing as multiplying by 10. So zero point 0.3 times 10 gives us 3x. The negative zero point 0.5 times 10 gives us 5y equals, and on the right side, negative 1.6 times 10 gives us negative 16. For the second equation, 0.5x times 10 gives us 5x. Negative 0.3y times 10 gives us negative 3y. And negative 1.6 times 10 gives us negative 16. So we want to now eliminate our x terms. So we find our least common multiple between 3 and 5. In this case, it's 15. So we want one of these terms to be positive 15, the other one to be negative. We chose negative as the top term. So we're going to multiply everything in that top equation by negative 5 and everything in the bottom equation by positive 3. So negative 5 times 3x gives us negative 15x. And let me erase this line here. What is that? So our first term, negative 5 times 3x, we got negative 15x. Negative 5y times negative 5 gives us positive 25y equals negative 16 times negative 5, we get positive 80. And then that last term, or the second equation, we're multiplying each of these terms by 3. So that's 3 times 5x, that gives us 15x. Negative 3y times 3 gives us negative 9y. And negative 16 times 3 gives us negative 48. Now we can add the top and bottom equations, and we see the x terms eliminate. 25y minus 9y gives us 16y. Carry down our equal sign, and on the right side, 80 minus 48 gives us 32. We divide both sides of this equation by 16. We see the 16's cancel on the left side. We get 2 as our y coordinate. So we've gotten our y coordinate. We now need to substitute to get our x coordinate. And we use the original first equation, which was 3x minus 5y equals negative 16. So where y is, we substitute positive 2. We'll get 3x minus 5 times 2. 5 times 2 is 10. So 3x minus 10 on the left side equals negative 16 on the right side. To solve, we're going to add 10 to both sides of this equation. The 10's will cancel on the left side, leaving 3x equals, and negative 16 plus 10 gives us negative 6. We're going to divide both sides of this equation by 3. The 3's cancel on the left side, leaving x equals negative 6 divided by 3 gives us negative 2. So here's our solution. Our one solution is negative 2, comma 2. And remember, we described those one solutions as being consistent and independent. All right, so that's the last example that we're going to work on dealing with the decimals and the fractions. We're going to look at a word problem, because some of your problems, you may not have the equation already written for you. You got to produce your own equation. So in this problem, we see the sum. What does this word sum mean? Remember, that means to add. So the sum of two numbers is 13. We don't know what those numbers are, so we're just going to call them x and y. We'll say x is the first number, and we'll say y is the second number. That sentence says the sum of two numbers is 13. How do I find the sum of x and y? I add them up. So x plus y equals 13. This is the equation we get based on this first statement. Now the second statement says the difference. Difference means to subtract. The difference, and we're talking about those same numbers, x and y, is 5. So here's the second equation, x minus y. We take the difference between x and y, and it equals 5. This is the equation we get based on the second statement. Now we're just going to solve this system of equations like we did in the previous examples. We got x plus y equals 13 as our first equation. X minus y equals 5 is the second equation. To solve, we could just add the top and bottom equations together because the y's will eliminate. And 1x plus 1x gives us 2x equals 13 plus 5 gives us 18 on the right side of the equal sign. Then we're going to divide 2 on both sides of the equation. We see the 2's cancel on the left side, leaving x, and it equals 18 divided by 2, 9 on the right side of the equal sign. So this is our first number. Remember x and y. So this is the first number. To get the second number, we just go back and substitute. We chose the first equation again. So that x plus y equals 13, and we substituted 9 here for x. And we get 9 plus y equals 13. Solve this equation by subtracting 9 from both sides of the equation. The 9's cancel on the left side, leaving y, and y equals 4. So here's our first and second numbers. It's 9 and 4. All right, in this next problem, we have the perimeter. Now remember what perimeter means. That means to add all sides. We also had a formula to find the perimeter of a rectangle. Since that's what we're dealing with in this problem, it says the perimeter of a rectangle. Remember that formula was 2L plus 2W, where L and W. L and W were the length and the width. So you're given this information. The perimeter of a rectangle is 42 feet. So that formula, that 2L plus 2W, remember that's perimeter, is 42. So we wrote 2L plus 2W is 42. The second statement says the length we know is the long side, L, is 7 feet more than means to add the width, which we're using W to represent the width. So here's our statement, and here's the equation we get based on that second statement. The length L is 7 feet more than the width, so W plus 7. These are our two equations, and we're going to solve this system. The first equation is 2L plus 2W equals 42. The second one, L equals W plus 7. We already have L, so we can use substitution. We'll substitute in that first equation. For L, we're going to substitute W plus 7. So we're rewriting the first equation, 2L plus 2W, but instead of L, we're writing W plus 7. Here we have to distribute 2 times W plus 7. So 2 times W gives us 2W. 2 times 7 gives us 14. We carry down the 2W, that's the rest of the equation, the equal sign, and 42. Now we're going to combine these like terms on the left side of the equation. 2W plus 2W gives us 4W. And this 14 we'll subtract from both sides of the equation. We'll subtract 14. On the left side, the 14's cancel. We'll get 4W equals, on the right side, 42 minus 14 gives us 28. So lastly, we're going to divide both sides of this equation by 4. The 4's will cancel on the left side, leaving W. Equals 28 divided by 4 is 7. So this is our width. To get our length, remember we had that formula, L equals 4W, or W plus 7. Now that we know the width, we just substitute 7 for W. And we'll get 7 plus 7, or 14, as our length. Now we have the length and the width of our rectangle. All right, so I'm going to stop the video here.